Welcome to today's class. Recall that last time I mentioned this result, which states that if we are given a convex fundamental domain for a Fuchsian group, satisfying that every point in its boundary is equivalent through a non-identity element to another point in the boundary, not necessarily different, because the element could be elliptic, then one could deduce, one could conclude that D is locally finite, that the convex fundamental domain is locally finite. Well, I was trying to prepare a lecture with a proof of this theorem, but I have to say that somehow the proof Beardon includes in the book somehow doesn't fully convince me. It could be, of course, that there's something I'm not fully understanding in his proof, and that is why it somehow doesn't convince me. So it could be as well just like my fault. But since I couldn't quite follow it, I'm going to skip it. Now, in the process of trying to prepare a lecture with the proof, I had to prove some statements that that Beardon, whose proof Beardon doesn't really include. So today's class I'm going to start with some scattered results. First about convex sets, then a nice theorem which states that any discrete subgroup of SL2R is countable, so that it cannot be uncountable. So it's either finite or has the cardinality of the natural numbers or the rationals, say. And then I'm going to move on to a theorem that relates somehow let's say, the structure of a fundamental domain to a generating set of the Fuchsian group in case the fundamental domain is locally finite. Okay, so let's start. So the first theorem, the first thing I want to prove is that if we are given a convex subset of the hyperbolic plane, then its topological closure in the hyperbolic plane is convex 2. For that, I'm going to prove first that the corresponding property holds for in Rn in Euclidean space. Then I'm going to deduce the property for the hyperbolic plane using the Beltramic lines model. So if a subset of Rn is convex, then its topological closure is convex. So recall that the definition of a subset of Rn being convex is that for every pair of points in the set, and every point in the closed interval 0, 1, the segment, the Euclidean straight line segment that starts in one of them and ends in the other, the whole thing is contained again in C. Right? So that's the definition of being convex in Rn. Which of course coincides with the convexity for the Euclidean Riemannian metric, right? So that is kind of that for every 2 points in the set, the shortest, the segment of shortest curve joining them is entirely contained in C. Okay, so let's prove it. So it all comes down to the continuity of this expression. So consider the function that takes pairs of vectors and any real number and forms the corresponding affine combination, right? So that lambda of the pair of vectors and t is this actually kind of this straight line because I'm taking the whole r as parameter. Mm-hmm. So, I mean, this is a polynomial expression in x, y, and t, so it is continuous by multivariable calculus. And so, well, I mean, also because of how the topology of this Cartesian product behaves, you know, this closure is equal to the Cartesian product of the closures. And so, lambda of this set is equal to lambda of this set, of course, because the sets are equal. And by continuity, lambda of this closure is contained in the closure of lambda of whatever is here before the closure. But this is C bar. This is the closure of C. Of course, all I need is this, but I actually have equality, and we are done, right? Because this, you see, this tells me that all the corresponding convex combinations of points of C bar are again in C bar. Okay, now from this, I can deduce that for any convex subset of the hyperbolic plane, the topological closure in the hyperbolic plane, so without joining any point at infinity whatsoever, is convex 2. It's a convex subset of the hyperbolic plane without infinite points, without points at infinity adjoined or attached. And the way to deduce it is to use the Beltrami Klein model. So in this course, I haven't spoken about this model of the hyperbolic plane. So let me mention some properties which I'm not going to prove, namely that the model as a set of points is the unit disk, the open unit disk, like the Poincaré disk, with the usual topology of the unit disk. But here the shortest curves in this model are precisely the segments of Euclidean straight lines contained in the unit disk. Now, how does one get to that model? I'm not going to say. One has to perform some projections in three-dimensional space to pass, say, from the unit disk, say, or from the hyperboloid to the Beltrami Klein model. So one advantage of this model is that in terms of shortest curves or geodesics, what you see what you get in a way, in the sense that the shortest curves are the Euclidean straight lines. That's an advantage. A disadvantage is that the model is not conformal, in the sense that in terms of angles, you don't see what you get. That is, if you have two shortest curves and then you look at their intersection and you measure the angle Euclideanly, that's not the actual angle between the shortest curves. It is not conformal. So in terms of angles, it is deceiving. Right? So one could argue that the upper half plane and the Poincaré disk, that they are somehow accurate when for measuring angles. They are conformal, but they are deceiving in terms of shortest curves, if you will. Whereas the Beltrami Klein model is deceiving in terms of angles, but accurate in terms of shortest curves, of see short curves kind of Euclidean, right, or in a Euclidean way. Anyway, so if you take such a convex set in the Beltrami Klein model, then it is convex uh, um, Euclideanly because the shortest curves here are precisely segments of Euclidean straight lines. Okay, so it's a topological closure. It's convex, Euclideanly convex. But the topological closure, according to the Euclidean topological closure, coincides with the topological closure with the hyperbolic topological closure. And so the topological closure, being convex in the Euclidean sense, is again convex for the model. And we're done. Okay, now the next kind of scattered result is this theorem that a discrete subgroup of SL2R and hence any Fuchsian group in PSL2R cannot be uncountable. Right? It cannot be very big in terms of cardinality. So what's the argument? Well, by now we know that a subset of, let's say, R4, is discrete if and only if it has the property that given any compact subset of R4, the intersection of my allegedly discrete subset with the compact set is finite. Okay, so consider R4 and consider a compact cube in R4 with center a vector in R4 with integer coordinates and sides of length equal to 2. This compact cube in R4 would intersect my discrete subgroup of SL2R, where here SL2R I'm seeing it as a subset of R4. My group would intersect that compact cube in only finitely many points. Okay, but now consider all the cubes with center in a point with integral coordinates and sides of length 2. Right? So those cubes cover the whole of R4, and gamma intersects each of those cubes in only finitely many points. So when I take the union of all those cubes, I get R to the 4. But what I'm doing is expressing the intersection of R to the 4 with gamma, which is gamma, as a countable union of finite sets. So gamma itself can only be counted. So I would say the argument is quite simple. So this is also quite nice. Okay, and now let's keep going with some let's say scattered results. Still coming all of this coming from some facts surrounding this proof in Beardon's book that I didn't quite fully follow. So let's say that we have our Fuchsian group and this fundamental domain V, of which we don't know whether it's locally finite or not. And so not knowing whether it's locally finite or not, we make these definitions. Namely, let's say that a point in the hyperbolic plane is regular if for some open neighborhood around the point, that open neighborhood intersects only, has non-empty intersection with only finitely many gamma images of the bar. And let's say that the point is exceptional if it's not regular. For instance, if you give me a point in V, then it is regular, right? So because it really is in only one gamma translate of the bar. Okay, and you see the exercise is that our fundamental domain is locally finite if and only if every point is regular. Right? So somehow these notions somehow allow to move from working with compact subsets of H with to working point by point and with the open neighborhoods around each point. Okay, and so you see somehow what Beardon's book argues is that he says that he proves that every point is regular, and so this is locally finite, right? And somehow what he says is I'm going to prove two things, namely first I'm going to show that the set of exceptional points is countable always. And second, I'm going to show that if non-empty, then it has to be uncountable. Then use the fact that gamma is discrete, is countable, and so on, and so and then somehow say, okay, then the set of exceptional points have to be empty because on the one hand it's countable, on the other hand, if non-empty, it has to be uncountable. Okay, but I like that. So let's finish for today with this very nice theorem, I would say, which is, if you start with a locally finite fundamental domain, then you can find a set of generators for your group in terms using that locally finite fundamental domain, right? And somehow using it in the obvious way, if you will, namely that if you consider the elements of gamma that don't move the topological closure of D very far away, that set generates gamma as a subgroup. Okay, and the proof is, I would say, quite nice. So given any point in H, of course, there exists an element of gamma that takes it into D bar, right? Because D is a fundamental domain. Now, of course, there could be many such gamma that take Z inside D bar. So let's analyze what happens when two of them take it inside D bar. Well, then, when I consider this composition, that composition obviously takes gamma 1 of Z to gamma 2 of Z. And so what you see, notice, this composition then takes this point of D bar to this point of D bar. So, which means that that this element satisfies this condition, right? That there's someone at the same time in D bar and in its image under D bar. Right? namely, let's say, gamma 2 of z. Okay, so but then you see this means that this is in the subgroup generated by gamma naught, I mean by this set, and so these cosets are coincide, they are the same. So this means that when I consider z, while there may be many gammas that take it inside the bar, they are at least well organized in the sense that they lie on the same coset. Uh-huh. So to each z, we can associate the corresponding coset. Right? So let's say here it would be the coset this gamma one. So here I didn't write this just kind of to avoid thinking that this one is normal in gamma. Right? And so what this means is, you know, the right congruence modulo this subgroup, which is, you know, two elements are related precisely in this hand. Okay. And now what I'm going to do is I'm going to show two things. One, that this function is locally constant. And second, that it is surjective. So I would say that it's obviously surjective. But in any case, if I show that it's locally constant and surjective, then the theorem will follow. Okay, so take any element of H again. So since D is locally finite, recall that we showed that there is an open neighborhood with the property that whenever that neighborhood intersects a translate of D bar, then Z was already in that translate, right? And this was, we used local finiteness because then we said, like, first take any compact neighborhood of Z, that one intersects only finitely many elements, only finitely many gamma translates of D bar, right? And then throw away those that don't contain Z, and for nz, instead of your original compact neighborhood of z, kind of take a smaller compact disk of positive rate. Right? So nz can be just the interior of that compact disk. Okay, so we have this. And what you see, for every element in this neighborhood, I actually have this, right? I mean, somehow you see, for any W in NZ, when you look at the gamma that takes it inside the bar, you see the gamma inverse actually has this property, right? Because W would be here and here, right? But here gamma. Okay, but then Z is in this gamma inverse of the bar, and so we apply this for that Z, right? And then P of W has to be the coset of gamma inverse, of the coset of gamma. I mean, the same gamma functions for Z, works for Z. Okay, so we see that the function is indeed locally constant because on this open neighborhood of Z it is constant, but its domain is connected. Okay? So locally constant, domain connected, it has to be constant. Okay, so it is constant. Okay, but I would say that this phi is obviously um, surjective. I mean, you see, take any coset, right? Okay, take that coset, and so how does that work? I mean, just take any x in d bar, apply gamma inverse, and then how do you take gamma inverse of x into d bar? Well, just apply gamma. And so this coset is phi of this point. So it is surjective. So you see a constant surjective function. Well, the image has to have only one element. But if this has only one element, it's because the subgroup by which you are taking the cosets, of which you are taking cosets, is the entire group, is the full group. And we are done. I mean, because then this means that the subgroup generated by this one is indeed the whole of gamma. Okay, now, I mean, H is connected, so somehow there is this, I would say, very challenging exercise, and kind of maybe less obvious than at first glance when one sees it, which asks whether one can lift the local finiteness assumption. So if you find a counterexample, I would be very eager to know about it. So that's it for today.